Hi and welcome to lesson 2 here in our electrochemistry unit. Here we're going to deal with spontaneous electrochemical processes and their applications. The most famous of which being this symbol that you all understand super well, batteries. Let's go in and take a look and see how this works. The major spontaneous system that you need to be aware of here in chemistry is the voltaic cell, also known as the galvanic cell. A voltaic cell is going to use spontaneous redox reactions to produce electrical energy. We can see this here. There's a redox reaction taking place between these two metals, which is producing a voltage as indicated by the voltmeter. In a voltaic cell, the redox reaction occurs in two half cells, with the reduction happening in one and the oxidation happening in the other. Let's go in and take a look and see what's happening here. We can start anywhere we want because it is a cycle, but let's just start with the electrons. The electrons are flowing from the more active metal to the less active metal through the wire. Copper and silver, we can use reference table J to tell us that electrons are going from the copper to the silver. As they move through that wire, that is the electrical current that powers whatever the electrical device is, what we call the load. In this case, it's just the voltmeter. Since copper is our more active metal and electrons are leaving that copper, that piece of copper is what we refer to as the anode. It's the electrode, or the piece of metal, where the atoms of that metal are oxidized. As copper atoms produce electrons, they are oxidized and they become ions entering into the solution. As the cell runs, that's going to cause the mass of the anode to decrease over time. It's not because the electrons are leaving and going through the wire to silver. It's because atoms on the surface of the copper electrode are losing electrons, becoming ions, and moving into solution. As the electrons arrive at the less active metal, which we're going to call the cathode, that is the electrode where reduction occurs, ions of the metal in the solution of that half cell are gaining electrons and plating themselves off onto the surface of that electrode. That is going to cause the mass of the cathode to increase over time due to the gain of atoms from the solution onto the surface of the electrode. This system only works due to the presence of the salt bridge. The salt bridge is going to allow ions to be exchanged between the two half cells, which is going to keep the overall system electrically neutral. If you think about it, as copper produces electrons, it becomes more positive. That would pull the electrons back and cause them to stop moving through the wire, unless we had some way of counterbalancing that increasingly positive charge. We do. That's the salt bridge. Anions, or negative ions, are going to move into the oxidation cell, the cell where the anode is producing electrons. Cations are going to move into the reduction half cell, the cell where the cathode is gaining electrons. As long as ions continue to move, the overall charge of the system remains neutral and electrons will continue to move through the wire, powering the load. This system is going to keep working until one of several things will happen. First, the anode could become totally disintegrated and stop producing electrons since all of the ions have moved into solution. The ions in the solution could be exhausted. If there's no ions to gain electrons that are moving onto the cathode, then the cell cannot continue to operate. Certainly, we could interrupt the wire by using a switch or just cutting the wire. That would interrupt the flow of electrons. And of course, we could remove the salt bridge or allow the ions in the salt bridge just to run out. Any of these situations will cause a voltaic cell to stop functioning. These are the parts of a voltaic cell and how it functions. It's really important that you understand them, what they do, and how they work. If you have any questions, now is a good moment to pause the video and write them down before we move on. Modern batteries have taken the chemistry that we see in a voltaic cell and have miniaturized it and made it much more efficient. The first batteries are what are called dry cells, which use a carbon rod and a zinc can as the two different electrodes and connect them using an electrolytic paste. These would run out relatively quickly, and so over time they've basically been replaced by alkaline batteries, which are the major batteries that you can buy in the store, your Duracells and your Energizers. They have the same size, but they can produce a higher voltage, and so they're much more desirable in modern commercial products. You can see the diagram of an alkaline battery over here. You are not required to be familiar with the individual parts. I'm just showing you the diagram so you can understand how the battery works. Of course, dry cells and alkaline batteries are both prone to leakage, which is why it's really important to remove the batteries from a device if you're going to let that device sit somewhere unused for a prolonged period of time. You don't want the batteries to leak because the contents of the battery, particularly alkaline batteries, are going to cause corrosion of the electrodes as the base in there interacts with the metal. Most of the modern technology that we use uses rechargeable batteries, which use a non-spontaneous redox reaction during the charging process to restore the battery back to a spontaneous current-producing state, which is what we use in the discharge process. The diagram below shows the charge and discharge cycle for lithium-ion batteries, which are probably the most common, most conventionally used batteries. They're the ones that we see in laptops and in cell phones and in devices that generally don't have removable rechargeable batteries. During the charge phase, ions are moved from the positive electrode to the negative electrode non-spontaneously, and then during the discharge, those ions are allowed to flow back spontaneously. Again, remember that you are not required to know the specific chemistry involved. I just thought it was interesting since batteries are so important in our lives. Similar to batteries are fuel cells, which work kind of like batteries, but they use fuel inputs, generally hydrogen gas and oxygen gas, to produce an electrical current. Oxygen gas moves into the fuel cell and it gains electrons at the cathode, which turns it from O2 gas into oxygen with a -2 charge. Hydrogen also moves into the fuel cell and produces electrons at the anode, which turns it into positively charged protons. Those positively charged protons then combine with the negatively charged oxygen ions to produce the waste product in a hydrogen-oxygen fuel cell, which is just water. Fuel cells are very interesting, and certainly many people are interested in using fuel cells to produce power in the future, but for right now there are some difficulties that still have yet to be resolved to make them commercially available. Another place where spontaneous redox reactions play a really important role is in corrosion, which is the spontaneous electrochemical degradation of a substance, which is incredibly costly in terms of industry as metals corrode very easily upon exposure to oxygen and water. During corrosion, the metal is spontaneously oxidized upon exposure to oxygen gas in the air. And this process is actually accelerated when that metal is exposed to water. If you think about all of the places in your lives where metal is exposed to oxygen and water, and consider the fact that they're all subject to corrosion, you can start to understand why this costs so much money to deal with. One of the major ways that we deal with it in terms of surface structures is just painting them. For submerged structures, things that are going to be in the water, like the hulls of ships or pipelines or tanks that are going to be in the ground, we'll use what's called a sacrificial anode in order to help slow the effect of the corrosion. The way that this works is by using a more active metal than the metal that the structure that we don't want to corrode is made out of, and connecting them with a wire. By doing that, you've now made the more active metal the anode instead of the less active tank or ship hull or whatever we're looking for, and so the more active metal will oxidize and spontaneously give its electrons as a protective current to the less active metal. Of course, as that anode disintegrates, it needs to be discarded and replaced over time. Does this make sense? If you have any questions about batteries or corrosion, don't hesitate to write them down before we wrap up. Thanks so much for watching our discussion of spontaneous electrochemical processes. Make sure you can do the following things here at the end. Make sure that you can identify the anode and the cathode in a voltaic cell. Make sure that you can draw and label the parts of a voltaic cell. Make sure that you can determine the flow of electrons and ions in a voltaic cell. Make sure that you can compare and contrast modern batteries with voltaic wet cells, how they're different in the sort of large picture sense. And finally, make sure that you can explain what happens during corrosion and how we slow the corrosion process. If you can do all those things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave them in the comments below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.